Hi, welcome to Dissolve Chemistry. Let us continue our discussion on this thermodynamics. In the previous video, we have discussed regarding spontaneous and non-spontaneous process. Okay, and followed by that, we have discussed regarding limitations of the first law of thermodynamics. And later, we concluded with the criteria for spontaneity of the reaction. In that, we have seen energy criteria as an important criteria for the spontaneity of the reaction. Generally, all exothermic processes were considered to be what? Spontaneous, and where the energy change means higher energy to lower energy the system is going to go. Okay. So, lastly, we put an question mark that the fusion of ice and evaporation of water, these two are the process which are endothermic but still they are spontaneous. So, which tells us that there are many processes. I have given just two examples I have mentioned. So that even though they are endothermic, they are spontaneous. Okay, just if you keep the ice at room temperature, that what happens, it melts on its own, and water from different water bodies are going to evaporate on their own at normal temperature. It is not at boiling point. If it is at boiling point, I said it is vaporization. Evaporation occurs, and all these processes are endothermic. So, but even then they are spontaneous. We can conclude with this. Energy is not the single criteria to be spontaneous. So, therefore, another criteria, very important factor, so that we will see is entropy. Say important thermodynamic function. Okay. So, it is the second criteria. Okay. So, for the spontaneity of the process. Prior to going for defining this particular term, let us illustrate that. We have seen that endothermic process only we will consider, and let us illustrate that one. See here, so in the ice, the constituent molecules are well organized, okay, or what we call it as, that is more ordered arrangement we are going to see. Now, when it fuses by absorbing energy, so it undergoes fusion, okay, and that fusion, what we are going to see, the disorderness means it converts into liquid form, where what happens, molecular arrangement is not as such it was previously in the form of ice, okay, water. Now disorderness has increased. Further, if you evaporate these, or if it undergoes evaporation, so then what happens, the molecules will be still more randomness, or organized randomly. So that is your gaseous state. Okay. So it means that the more order to more disordered. Okay. Order to disorder, or less randomness to more randomness. And if it is so happening, then also we call it as what? It is going to occur spontaneously. Okay. When the system is going with what? We call it as what? Increase with its randomness, then that process is said to be spontaneous. So therefore, that spontaneity or the measure of this disorderness, increase in the disorderness or randomness of the system is nothing but what? Your entropy. So let us define this one. Okay. It is the measure of randomness or disorderness of the system. Okay, we will see the different criteria of entropy for spontaneity of the process. Okay, so it is the measure of randomness. Now the next, it is a state function. So what do you mean by state function? Already we have defined and we explained in greater detail if you watch our previous video. Okay, please watch that one. State function meaning is what? Its value is always going to depend upon the initial and the final state of the system. Say for example, S1 is the initial state of the system, then S2 is the final system. Okay, so therefore, so system, when it goes from initial state, its entropy is taken as S1, and system, if it goes to final state, then we call it as entropy as S2. So therefore, always remember, as it is a state function, it is not possible to measure absolute value. Okay, it is a state function, and the entropy, absolute entropy is not possible to determine. Absolute entropy, okay, we cannot determine. We cannot determine. Okay, so then what we are going to determine? So it is possible to determine change in entropy. Okay, so that we call it as what? Delta S. So delta S is equal to S2 minus S1, final minus initial entropy of the system. And you should remember, it won't depends upon the path or the way the change has been brought in the system. If the system is isolated, okay, your system is isolated, then what we are going to see is the change in entropy for isolated system will be, if it is positive, then the process will occur spontaneously. Okay, the process in isolated system will be spontaneous when the entropy change of that particular system is positive. Okay, so that one point you should make note of. The mathematical form of entropy. Okay, so mathematically we are going to define this entropy. Okay, that is change in entropy is equal to S2 minus S1, which in turn is equal to Q reversible by T. Okay, Q reversible, it implies that the amount of energy utilized by the system to increase its randomness, okay, and T is temperature, right? Now let us understand with one numerical example. We will understand very easily. So that is, a system is there. Okay, so your system is at, say for example, 300 Kelvin. Okay, and this system is going to absorb 900 joules of energy. Q is equal to 900 joules. So now all this 900 joules is being utilized by the system at this temperature to expand. Okay, only for expansion this particular amount of energy is being utilized by the system, if you consider. So then what happens? The change in entropy for this will be what? Delta S is equal to what? So 900 joules by 300 Kelvin. Now what it turns out to be? So it turns out to be what? Delta S is equal to 3 joule per Kelvin. Now let us understand the meaning of this. See, when you supply 900 joules of energy to the system at 300 Kelvin, then per Kelvin temperature, the 3 joules of energy is being utilized by the system to undergo what? Or to bring the change in its entropy, we call. Means 3 joules of energy per Kelvin temperature being utilized by the system to bring in the change of entropy. Okay, so now how it depends upon the temperature? Is it going to be varying with a different temperature, or it remains constant? That we will see. So you keep it as it is. You take the same system at another temperature, that is 450 Kelvin. Okay, now you take the system is at temperature T is equal to 450 Kelvin, and assume that it absorbs the same amount of the energy. Okay, and it is using for the same expansion, okay, or to increase its randomness we call. So now you calculate what happens to your delta S. Delta S is equal to 900 Kelvin, joules divided by 450 Kelvin. So now what happens? It turns out to be delta S is equal to 2 joule per Kelvin. What is the meaning of this? Here when the same system, when it is at 450 Kelvin temperature, then the amount of energy utilized by the system to bring in change in its entropy per Kelvin is, that is 2 joules. Okay, so here 2 joules of energy is used to increase its entropy or bring change in the entropy of the system. Here it is 3 joules. What does it implies? As you are rising temperature from 300 to 450 Kelvin, okay, so the entropy change here, it was 3 joules per Kelvin and now it has changed to 2 joule per Kelvin. Meaning is what? As the temperature increases, the change in entropy of the system is going to decrease even if it absorbs the same amount of the energy. Okay, so therefore we will draw the conclusion for this, right? See here, delta S increases as the temperature decreases, or temperature is lower means change in entropy will be high, and change in entropy will be low at a higher temperature. When the temperature is high, okay, high, then your change in entropy will be low, and change in entropy will be high when the temperature is low. So please make note of this. Okay, generally MCQs will appear on this particular concept. Okay, then next we will move on to the important aspect. So that is, here only we will make note of this. When the energy is evolved during the process, okay, suppose amount of energy is being evolved, right? So then what happens to the entropy change of the system? Okay, say for example, if the process is exothermic or heat is evolved, okay, then entropy of the system will be decreasing. Entropy decreases. When heat is absorbed, then change in entropy increases, or entropy of the system increases. Okay, so that is the condition you should remember. When heat is evolved during the process, then the entropy of the process decreases. If the heat is absorbed by the system during the process, then entropy change will increase. Okay, so this point you should make. Both are very important aspect. Okay, so now we are in position to define second law of thermodynamics based on this entropy. Fine. Second law of thermodynamics. Okay, so this based on this entropy, there are you should remember that the second law of thermodynamics, there are different statements we find. Okay, time by time we will define those things. So here we are going to define this second law of thermodynamics, or we will give the statement for this based on entropy change. That is how that the total entropy of the universe, total entropy of the universe is sum of the entropies of the system and surrounding. Okay, the total entropy of the universe is sum of entropies of the system and surrounding. That's how we are going to represent delta S total, or you call it as universe. Okay, so that is equal to delta S of the system plus delta S of the surrounding. Okay, so now the total change in entropy of the system will narrate either the process is spontaneous, non-spontaneous, or it is going to attain an equilibrium as follows. Let us see that one. If the total entropy of the universe, if it is positive, okay, so if the total change in entropy of the universe is positive, means increases during the process, then that process is said to be spontaneous. Okay. Then if the total change in entropy of the universe, if it is negative, then that process is said to be non-spontaneous. Then last one is when the change in entropy of the universe is 0, okay, equals to 0. So then we call it as what? The process is at equilibrium. You should remember all these three conditions, which are very, very important. Okay, total entropy of the system, total entropy of the universe, if it is positive, okay, of the system may be positive, may be negative, of the surrounding, whatever it is. Overall entropy, if it is positive, means total entropy of the universe, if it is positive, then the process is said to be spontaneous. Okay, so now the change in entropy either of the system or the surrounding, either it is positive or negative. Overall entropy of the system, if it is negative, then it is called non-spontaneous process. Okay, if the entropy of the system and surrounding, sum of these two, if it is equal to total entropy of the universe, both are same, so then if it is equal to 0, so then we call it as what? That particular process or the reaction is at equilibrium position. Okay, so this is how we are going to make the conditions of entropy, and that is how we are going to define second law of thermodynamics. Okay, then next we will move on to another aspect of this entropy. So in the previous example we have said that the 3 joules of energy is being utilized by the system per Kelvin. Okay, so per Kelvin to increase or bring change in the entropy of the system. Okay, so means only to increase its randomness or disorderness or to spread. Okay, so that much amount of energy is being utilized by the system. Now, do you think that that energy is available for to do the work? No, because that is, especially it is being utilized for what? Doing expansion, or we call it as what? To spread or to increase its randomness. So therefore that particular energy is always, it is not available for to what? Do the useful work or to get the useful work. So therefore we call that as delta S is equal to Q reversible by T. So therefore that Q amount of energy absorbed to bring the change in entropy at a given temperature is said to be what? Unavailable energy. Okay, unavailable means we cannot draw the useful work from that. So therefore we call it as what? Unavailable energy. This is very important. You should make note of this. Okay. The next is so in the second law of thermodynamics, as we have defined by using this entropy change, there we have said that the entropy of the universe, if its change is positive, then we called as what? The process is said to be spontaneous. Okay, so now the thing is that most of the reactions we carry out in a open vessel. Okay, many of the process will occur in a open vessel. The system will be open, or even it may exchange heat with the surrounding, and that means it is in contact with the surrounding. It is not always isolated. So in that case what happens? Either if the decrease in the entropy of the system occurs, increase in the entropy of the surrounding occurs, or always our system will be in communication with the surrounding. So therefore entropy is also being exchanged between the system and the surrounding. Now the question arises, if you want to calculate or to get the total entropy, again we need both the entropies of the change in the entropies of the system as well as the surrounding. Of course we can somehow determine the entropy change in the system, but what about the surrounding? That how much change has occurred in the surrounding, it is very difficult to determine. Okay, so therefore to fix that the spontaneity of the process, entropy is not enough, because we cannot determine the total entropy during the reaction or the process. So therefore it is necessary to define another function, so which is independent of this total entropy, okay, where we are not going to look into the change in the entropy of the surrounding, only we will see into the change in the entropy of the system, and that new function we call it as what? Gibbs free energy. Okay, regarding this Gibbs free energy we will see in the next video. So please subscribe our channel and don't forget to like. Okay, thank you for watching.